Every phone and laptop you own runs on a number most people never think about. A standard DRAM chip from Samsung or SK Hynix needs about 200,000 electrons to reliably hold 1 bit of data. A team at Fudan University in Shanghai just built a working memory chip that stores that same bit using exactly 1 electron, not a rounded estimate. 1. The paper was published in the journal Science on July 16th, and it survived peer review, which matters, because for almost 30 years, this exact idea has quietly wrecked every serious team that tried it. To understand why that gap is such a big deal, you have to know what a memory cell actually is underneath the branding, and who's behind this particular one. Zhou Peng, the microelectronics professor leading the Fudan team, has spent years chasing exactly this problem, publishing a steady run of results that kept inching the field closer without quite reaching it. The kind of track record that makes a claim like this one worth taking seriously instead of dismissing on sight. Every bit of information sitting in a phone, a laptop, or a server rack inside a data center is really just a tiny reservoir of electric charge. Fill that reservoir with electrons, and the cell reads as a 1. Drain it, and the cell reads as a 0. A chip does this billions of times a second, and the whole system depends on being able to tell a full reservoir apart from an empty one without ever getting confused. Engineers call that confusion noise, and for 70 years, the fix has stayed the same. Throw more electrons at the problem, enough that the signal becomes impossible to mistake. It works. It has always worked. And it also means every memory cell in every server rack humming inside a data center right now is burning far more charge than physics actually requires just to stay reliable. There are really 2 kinds of memory doing this job inside your devices, and they trade off against each other. DRAM is fast. It's what a processor reads from constantly while it works, but it forgets everything the instant power drops, which is why closing your laptop lid without saving still risks losing an unsaved document. NAND flash, the kind inside your phone and your SSD, keeps its data with the power off, but it writes far more slowly, typically in the range of microseconds to milliseconds per operation, rather than nanoseconds. Engineers have spent decades chasing a memory that combines the speed of DRAM, the permanence of flash, and a lower electron cost than either. Because right now every device you own is a compromise between those 3 things, a trade-off baked into the physics long before any of us bought our first phone. Guiyi is a proof that the electron cost part of that compromise has a hard floor, and that floor is 1. So why not just use fewer electrons and save the power? Engineers have wanted exactly that since the 1990s, and here is the wall they kept hitting. An electron carries an almost unimaginably small amount of charge, so trying to detect whether 1 extra electron is sitting inside a cell is a lot like trying to spot the ripple from a single drop of water landing in a swimming pool. The drop is real, the effect is real, but it disappears inside every other disturbance already happening in that pool. The waves from someone swimming, the vibration from the filter running in the background. Inside a chip, that disturbance has a name: fringe capacitance, unwanted electrical coupling between parts of the circuit sitting close together. And here is the part that makes it so brutal. Shrinking a device to pack in more memory doesn't fix this problem. It makes it worse. The components move closer together, the stray coupling gets stronger, and the already faint signal from a single electron buries itself even deeper in the noise. Every attempt at fixing this by simply making the device smaller runs face first into the very physics it was trying to exploit, which is why so many labs quietly abandoned this direction and went back to the brute force approach of just adding more electrons. That's the exact trap that has kept single-electron memory a laboratory fantasy for a generation of engineers. This isn't a new dream either, and it isn't a story that only involves China. In 1997, a team at the University of Minnesota, led by researcher Guiyi, ran the first real test of it and actually pulled it off in a lab at room temperature with no exotic supercooling required, publishing the result in the same journal, Science, that Fudan just published in. They detected the presence of a single stored electron, a genuine milestone at the time. But the signal it produced was only about 55 millivolts, barely a whisper against the electrical noise surrounding it, and the charge stayed readable for roughly 5 seconds before it faded back into the noise floor. A signal that fades in about 5 seconds isn't something you can build a working chip around. So that 1997 result sat in the literature for the next 3 decades, doing 2 jobs at once. Proof the idea was physically possible, and proof it was nowhere close to practical. Through the late 1990s, corporate labs at Hitachi, NEC, and Toshiba in Japan all published their own attempts at room temperature single-electron memory, chasing the exact same wall. Nearly every one of them ran into the same fringe capacitance problem and quietly stalled. This was never a race one country was running alone. It was a genuinely global chase that most of the industry had simply given up on by the time Fudan picked it back up. Part of why the chase stalled is that one electron carries the smallest amount of electric charge that can physically exist. Charge comes in fixed units, and an electron can't be split into half a charge or a third of a charge. A memory cell that reads a single electron is not an incremental improvement over one that reads 200,000 of them. It's the actual floor, the last stop on a 70-year road of shrinking how much charge it takes to store a bit. There's nowhere left to go below it. That's part of why the science reviewers who checked this paper, and outlets like the South China Morning Post afterward, kept reaching for the phrase Holy Grail. It isn't exaggeration. It's a description of where the road ends. The team that finally closed that gap didn't appear out of nowhere. This same Fudan group has been on a run. In April of 2025, they published a graphene-based flash memory device called POX in the journal Nature, and it programmed a single bit in 400 picoseconds, which works out to about 25 billion operations every second, replacing silicon channels with a 2-dimensional graphene structure they call Dirac graphene to move charge almost frictionlessly. The mechanism behind that speed had its own name too, 2-dimensional enhanced hot carrier injection, essentially finding a much lower energy barrier for charge to cross by exploiting how thin the graphene channel is, the same atomic thinness that would later help tame fringe capacitance in Guiyi. Joe Peng described the leap himself at the time. His words were that the device could work 1 billion times in the blink of an eye, while an ordinary USB flash drive manages about 1,000 in that same blink, and the previous world record for that kind of switching speed sat around 2 million operations per second before POX blew past it. For comparison, the fastest DDR5 memory on the market today still needs around 12,000 picoseconds to write a single bit, so POX was already running roughly 30 times faster than commercial DRAM while also keeping its data after the power cuts out, something DRAM has never been able to do. A few months later, the same lab followed it with something called Changjing, a framework for fusing that atom-thin, 2-dimensional memory directly onto ordinary silicon electronics, described as the first working 2-dimensional silicon hybrid flash chip. By the time the single-electron paper landed in July, this lab had already shipped 2 separate hardware firsts inside about a year. Guiyi, the name they gave the new device, translates loosely to return to one, and it was their 3rd act in 12 months. Here is what they actually changed to make Guiyi work. The device is built almost entirely from materials only a few atoms thick. The current runs through a sheet of graphene, a single layer of carbon atoms arranged in a honeycomb pattern, the same material behind POX's speed record, chosen because it lets charge move through it with very little resistance, and because it can be manufactured in sheets literally 1 atom deep. That thinness is the reason the whole approach works, since fringe capacitance is fundamentally a problem of how much material sits around the electron waiting to interfere with it. layered with thin insulators and arranged in what the researchers call a coplanar drain channel source structure. That geometry sounds abstract, but the purpose behind it is simple. It was engineered specifically to choke off the fringe capacitance that drowned the 1997 result and every serious attempt after it. Instead of fighting stray electrical coupling after the fact, the flat atom-scale layout removes most of the places that coupling had to hide in the first place. That's half the fix, and on its own, it would not have been enough to get a usable signal out of a single electron. The second half is where it gets genuinely strange. Every time a single electron entered or left the storage region, the device's electrical response jumped by one clean, repeatable step. But the researchers also noticed something else happening at the exact same moment. The instant the first electron settled into place, it changed the local conditions inside the device just enough to block a second electron from immediately following it in. Engineers call that self-limiting behavior, and it turned out to be the missing piece the whole field had been circling for decades without quite naming it. Physicists have a name for the underlying effect too: Coulomb blockade, where one electron already sitting in a tiny confined space repels the next one hard enough to keep it out entirely until the first one leaves. Guiyi's design leans directly on that repulsion instead of fighting it. It meant the device could not accidentally load 2 or 3 electrons in a rush and blur its own signal into noise. It naturally moved through single electron states one at a time, on its own, which is exactly the discipline a working memory cell needs. And it's a genuinely quantum mechanical effect, not something engineers designed in directly line by line. They found it already happening inside their own device, then learned to steer it, which is arguably the more impressive part of the whole paper, since discovering a useful quantum effect you did not deliberately engineer is a very different skill than designing one from scratch on a whiteboard. If breakdowns like this one are useful to you, subscribe. This channel walks through the real engineering behind China's breakthrough technology every week, not just the headline version everyone else is copying. Guiyi is also not the first device to claim it could handle single electrons at room temperature. Through the late 1990s and into the 2000s, several teams built devices with names like quantum dot flash memory and nanocrystal memory that claimed some version of the same trick, and more than one of them ran straight into the same wall Guiyi is running into now, a workable signal that only showed up at an operating voltage far too high for any real chip. History has a way of repeating the same failure mode in this specific corner of physics, which is exactly why the honest correction later in this video matters as much as the achievement itself. Now for the proof. Because a claim this specific needs numbers this specific. The researchers could not exactly watch a lone electron walk into the device, so instead they measured the tiny shift it caused in the voltage needed to switch the memory on. Because they knew the device's electrical properties precisely, they could calculate exactly how large that shift should be if a single electron was responsible, and the measured number matched the prediction almost exactly. About 0.5 volts. That's roughly 9 times stronger than the original 55 millivolt signal, and the signal rose and fell in matching half-volt steps every single time an electron was added or removed, with background noise measuring about 10 times smaller than the signal itself. Those repeatable, precisely sized jumps are the actual evidence the device was handling electrons one at a time, rather than in a blur. The proof isn't a photograph of a lone electron sitting inside a trap somewhere. It's a chip behaving exactly like the math predicted it would, over and over. And then there's the retention problem that killed the original test. Guiyi held its single electron state through a 5,000-second experiment, about 83 minutes, with the team's own data suggesting the states could last for years once the design matures further, which would put it in the same league as the flash memory already sitting in your phone right now. Go back and put those two numbers side by side. A 55 millivolt signal lasting 5 seconds in 1997 against a 0.5 volt signal projected to last years out of the same underlying physics in the same journal. essentially 3 decades apart. That's the actual distance this field has traveled, measured in numbers instead of adjectives. There's a second discovery buried in the same paper that almost nobody covering this story mentioned. Alongside the programming voltage quantization and the self-limiting behavior, the team observes something they're calling a density of state scissors effect, essentially a way the device can cut off a specific quantum state on command. Density of states, in plain terms, is just a map of which energy levels an electron is allowed to occupy inside the material. Guiyi's structure lets the researchers reach into that map and sever specific levels the way a pair of scissors cuts a line, controlling exactly which quantum state the trapped electron can settle into. That opens a real path toward a single memory cell holding more than 1 bit at a time, multiple distinguishable electron states instead of just full or empty. The same idea that lets modern flash drives pack multiple bits into one physical cell today, except taken all the way down to the level of individual electrons instead of larger charge packets. If that scales into a real product, density stops, depending only on shrinking the chip further, which happens to be the part of the semiconductor roadmap running out of room the fastest as transistors approach the size of individual atoms, a wall the whole industry has been racing toward for years. So does this go into your next phone? No. And here is the part every viral headline conveniently skipped over. Guiyi needed programming pulses of roughly 29 to 30 volts to actually write and erase its single electron states. A real phone chip runs on something closer to 1 volt, and even POEX, the same lab's earlier speed record holder, only needed about 5 volts to operate. 30 volts would not just drain a phone battery in minutes, it would require driving circuitry that does not fit inside anything you could hold in one hand. So the voltage gap on Guiyi is not small. It spans multiple orders of magnitude beyond what any consumer chip's driving circuitry is built to handle. And closing it means redesigning that circuitry around the device before it could ever survive inside a phone or a laptop. Work that typically takes years, even when the underlying physics is completely solid. On top of that, this is one working memory cell tested carefully in a lab, not a memory array with millions or billions of identical cells proven to behave the same way side by side. Getting from one working cell to a real chip means every one of those billions of cells has to trap and hold its single electron with basically identical behavior, cell after cell, wafer after wafer, at a manufacturing yield high enough to be worth building a factory around. That gap between one working device and a uniform, mass-produced array is the actual engineering mountain sitting between a paper in science and a shipping product. And it has quietly killed more promising lab breakthroughs than any single technical flaw ever has. The physics floor is real, and Fudan's own team is upfront that the commercial chip is still years of engineering away from anyone's pocket. Which raises the obvious question: why is a lab demo running at 30 volts getting called a breakthrough for breaking AI's memory bottleneck by outlets like the South China Morning Post? Because that 200,000 electron number is a real reason AI infrastructure has become one of the fastest growing consumers of electricity on the planet, and every chip maker on Earth is watching for a way to bring that number down. The International Energy Agency puts global data center electricity use at around 415 terawatt-hours in 2024, and projects that figure to nearly double to around 945 terawatt-hours by 2030, slightly more than the entire country of Japan currently uses in a year. AI-focused facilities inside those data centers are growing their power draw even faster than the industry average, with the IEA logging a 17% jump in overall data center electricity demand in 2025 alone, and a 50% jump specifically at AI-focused facilities in that same year. And every one of the electrons, the current generation of DRAM, burns through to store a single bit, adds up at a scale like that. This is also a real infrastructure bottleneck. A refrigerator-sized server rack running the newest AI accelerators can already draw power in the range of what dozens of households use at once. And grid operators from Virginia to Ireland are openly warning that new data centers are showing up faster than local power grids can supply them. In Ireland specifically, data centers already account for roughly a fifth of the entire country's electricity use, a share the government's own regulators expect to keep climbing before the end of this decade. None of that gets solved by one paper out of Shanghai. But every electron Guiyi's approach eventually removes from a DRAM cell is an electron. A power plant somewhere doesn't have to generate in the first place, multiplied across billions of chips. Push the electron count toward its theoretical floor and the payoff stops being abstract. Server racks that need less cooling. Phones that could eventually run full AI chat models locally, instead of sending every request out to a data center, without the AI losing track of the conversation halfway through, because it ran out of local memory to hold it in. Joe Peng isn't treating any of this as pure academic curiosity either. He's already planning to spin the technology out into his own company within the year, with a rough 5-year target to get it into real production, following the same lab that took POEX from a Nature paper straight into active scale-up work within months of publishing it. That track record is exactly why this paper is getting taken seriously by people who don't usually get excited about a single device in a single lab. A group that ships a world speed record 1 year, a silicon integration framework the next, and a working single electron memory. The year after that is building real momentum. Solve the memory wall, and you have only solved half of what's actually slowing AI down. A chip can remember everything perfectly and still sit there waiting on the processor, doing the real thinking. The silicon running the actual calculations behind every response. Memory and computation have always been two separate fights inside a chip, and China closing the gap on one side doesn't automatically close it on the other. Right now, nearly all of that second fight, the actual thinking, still runs through chips built by one American company sitting on a market valuation north of $5 trillion. What China is building to break into that side of the fight is a very different kind of chip, a processor rather than a memory cell, and it's already running inside real data centers today.